Section 7.10 is called power triangle. And what we can do is we can take this right angle relationship between active, reactive, and active apparent power, apparent, active, and reactive power, and we can create a graphical tool to help us solve problems. And we call that the power triangle. And so let's look at what that looks like. And we can see that in this figure 712 in our textbook. So this relationship, this right angle triangle relationship of apparent squared equals active squared plus reactive squared, that is something that goes back, to what, middle school kind of hypotenuse solving of the right triangle. So, this would be our hypotenuse, and we're going to call that our apparent power. Okay, so this is apparent, and it's abbreviated with the S, of course. And then what we also have is the active power, and it's given here. And then what we additionally have is the reactive power, and it's given as the vertical representation. But altogether taken as a whole, we call this our power triangle. Okay, and it's a very useful graphical method to solve these power problems. Okay, so the description of this says that the active power that's absorbed is going to be shown as positive, drawn horizontally to the right. Okay, so this would be active power absorbed. Okay, now there is a situation where active power is delivered by a circuit or device, and it's considered to be negative. And if we had that situation, it would be drawn to the left. Now, I am trying to think of something relevant that would show that, and right off the top of my head, I'm having trouble thinking about what that would be. But anyway, this is, think about this as being the 0 point, right? And delivered would be to the left, absorbed would be to the right. All right, and that's just kind of arbitrary, just a way for us to understand things. Then reactive power that is absorbed by a circuit or device is considered to be positive. All right, so in this case, this is what we're seeing here. This is reactive power absorbed. And then, and we think about what, an inductor absorbing a reactive load. And then it can also be drawn down. And in that situation, reactive power is delivered. And we talked about how that occurred with a capacitor and all. So we could have this, and normally what happens, or a lot of times what happens, we'll have a combination, of the X of L and the X of C, or in this case, we're talking about power Q of L and Q of C, and whichever one is greater determines the ending relationship in terms of the direction of how it's drawn. So if it's primarily inductive and absorbed, it's going to be drawn north. If it's primarily capacitive and delivered, it would be drawn south. And this power triangle that we're looking at here, it's actually labeled or given these values that we looked at in the example 7.8. Okay, and if you look back at example 7.8, it said it was a single phase motor drawing current of 5 amps from 120 volt 60 hertz line, and the power factor of the motor is 65%. Okay, and then it went through this derivation of determining what the apparent power was and the active power and then the reactive power. So with this problem, here's the 390 watts that we determined in example 7.8, and go back and check that. And then the Q is the 456 var, and then the sum of those, right? The sum of those would be the 600 volt amps, or the apparent power. Now, I'll read this, and in some ways this is not important, but it says the power components of S, P, and Q look like phasors, but they're not. However, we can think of them as conventional vector. A vector is something that has magnitude and direction. The concept of the power triangle is useful when solving AC circuits that comprise several active and reactive power components. And we'll go through some of these problems later, and we'll just see how simple the power triangle can make some very complex problems are able to solve very simply. Okay, that's it for 710.